All right, so let's open the Visual Surveying document. Where is it? Okay, I might have to download it myself. I don't know where it is. All right. Okay, so we're going to discuss visual surveying. So I hope you guys have read through this and gotten a basic idea at least, but we'll go through the derivation of this step by step and try and understand it. So visual surveying situation is basically where you have a robot arm or something like that, right? We kind of did something similar in our first quiz where we have a camera. So either attached, oops, sorry. I hate this little thing that keeps popping up when I move my, try and move it away. Hold on. Yeah. Okay, so you can have a situation where you have the camera kind of stationary, right? Or you can have a camera attached to the arm itself, right? You try to achieve some sort of control of this arm based on the input you're getting from this from these sensors, right? So that's really the visual surveying kind of scenario that we're dealing with, right? So you can see here the vision data may be acquired from a camera that is mounted directly on a robot, in which case motion of the robot induces camera motion in itself. Or the camera can be fixed in the workspace so that it can observe the robot motion from a stationary configuration, right? So visual surveying is the name of the problem that incorporates all of this stuff, right? So the entire idea here that we're going to do, that we're trying to achieve, is we are going to look at, we're going to try and derive this problem in a more in a very generalized kind of format so that it can apply to a lot of different types of visual feature detection, right? So you guys saw that one of the first steps that we would do to kind of recognize an object, and you probably are having to deal with this in your projects as well, is you have to detect some sort of features of the object, right? So in the case of Ying Chu's, like human or whatever, you need to kind of detect that this person is a human, so you'll have to run some sort of detector to kind of figure that out, right? So we learned about detectors like SIFT, SURF. You could have a deep learning network, right, that detects these features, and ultimately what you're going to get is a bunch of pixels, right, in the image. You're going to say that this pixel, this pixel, this pixel, let's say it's a square or something like that. You will get that this pixel, and this pixel will represent the edges of the square or whatever like that, right? So ultimately you will get pixel values, but what you will what those pixels values are going to depend on what the feature detector you picked, or like what sort of features are you trying to detect, right? So we are going to derive this whole thing in a very generalized form. So we are going to call whatever those features are S, right? So S is going to be basically kind of a generalized what do you call it, feature that we're going to look at, right? So M is going to be the pixel values, right? So the raw pixel values that we kind of detect or whatever, right? A is basically the camera parameters. That is like the focal length, the principal point values and things like that, right? So we'll actually look at an example here later on, right? About what we're really talking about when we say S and stuff. But for now, just think of S as like the features that we want to track, right? So let's take a simple, actually to make this easier, let's take a simple example. Let's say we are looking at a square, right? A cube, just like in our quiz, right? We have a cube, right? And then we take a photo of this cube, right? And in this case, our features that we can use are the edge points, right? So we can use a Harris corner detector or something like that, right? So S is our current location of these features, for example, right? But S can be whatever, right? Like depending on your scenario, S can be like a SIFT descriptor or a surf descriptor or whatever, right? Which is why we're using this generalized notation called S, right? Which can encompass any sort of detection, any sort of feature that we are interested in, right? S can even mean, for example, 3 of these all together, right? That can be one feature, right? Or for example, if you're dealing with a person, maybe you have a really good eye detector that detects the whole eyes of the person, right? So that will be your S in that case, right? But to make things simple, let's take each of these corners as your S, right? So that is what we are currently detecting. S star is where we want those features to be, right? So imagine imagine the scenario where you have a robot arm trying to pick up a cube, right? So when we are starting off, let's say this is what the image looks like, right? But we know to pick this up, what you end up, your image should look like this, right? Since the robot arm has to go close and pick it up, and let's say the camera is attached here, we kind of have an idea of what the image is going to look like. So when it comes closer, maybe the cube has to align like this nicely in the image and become larger, right? And so we have an idea of where the pixel values should end up at, right? And that is what we call S star, right? So S star is essentially that reference value that we have in our control system, right? This is where we want our features to end up, right? So just like in PID control, we create an error term, right? So our error term is going to be S minus S star. So S star is where we want our features to be. S is where it currently is, right? And so we have an error term. Okay, so what we're going to do is we're going to control, we're going to think of a situation, for example, let's imagine we can control the velocity of this. So what we're going to design is a simple velocity controller, right? So imagine we have the velocity of this arm's gripper, right? And let's think of a situation where the camera is attached to the arm itself, right? So in that case, the camera's velocity is the same as the gripper's velocity, right? Because they're attached together, right? But ultimately, what we're trying to control is the gripper's velocity, right? Because we are trying to get the gripper to come close here and pick this up, right? So what we need to essentially do, just like in the PID controller, what did we do? We found a relationship between the parameters that we can control, which is our input, and this error, right? And we created like a KP term here and a KI term to that error, and we controlled our input in a way that is related to these errors, right? So that's pretty much what we have to do here as well. What is our input? Our input is going to be the velocity of this gripper, right? On a higher level, right? On a lower in-depth level, it's going to be the motor controls and all that stuff, right? But from a kind of abstracted high level, what we essentially ultimately want to control is the velocity of this gripper or the velocity of the camera, right? Because if the camera is attached to this, it's the same thing, right? So what we essentially want to do is find a relationship between this error, right, and the velocity of the camera. And that's pretty much what we're trying to achieve, right? So if the gripper is moving, right? If there's a velocity to the gripper, right, what's going to happen to your features? Your features are also going to have a velocity, right? They're going to start changing, right? Your features, as this is moving, your features are also going to change, right? So the relationship between this velocity and your features is given by this equation, right? S dot is basically the rate of change of your features, right? And there should be some sort of relationship between these two, right? And that relationship is mapped by this LS matrix. So obviously when your arm is moving at a certain velocity, so will your features, and that relationship is captured by this LS matrix. We don't know what this matrix is yet, right? But we know that there has to be some sort of matrix that maps the velocity to those features, right? And this matrix is what we call the interaction matrix, right? So what the interaction matrix does, sorry, I think I wrote it the other way around. The interaction matrix is the relationship between the velocity and the change in features, right? So as the velocity changes, it affects how the features are changing. That's obvious. And that relationship is captured by this LS matrix, which is what we call the interaction matrix, right? So we have this relationship, right? So we have a nice relationship between the changing values of the velocity and how it affects the change in features. But what do we need for the control? We need to relate this VC with the change in the error, right? Kind of like in the PID situation. So to find this relationship, what we do is we differentiate this with respect to time. If we differentiate this with respect to time, you get E dot is equal to this to become S dot if we differentiate everything with respect to time, right? And you can see that this S star is a constant, right? This is our reference. It's a constant. It's not going to change. So if we differentiate a constant with respect to time, it just becomes 0, right? So what we're going to get is what we're going to get is E dot is equal to S dot, right? So now we have this relationship S dot equals LS equals VC, and now we are seeing that the change in the error is the same as the change in S dot. So instead of S dot, we can easily replace this by E dot is equal to LS VC. So now we have a relationship between the change in error and the velocity of the moving arm, right? And that's what they've written here, right? So if you differentiate this error with respect to time, we see that the change in error is equal to the change in the features. So we can simply replace S dot with E dot here. And now we have a direct relationship between the error and the velocity. But that relationship is governed by this interaction matrix who we don't know, right? So they've said LE here, and then they said LE is equal to LS because of this relationship, right? So now we have this relationship between the velocity of the control, velocity of the gripper or the velocity of the camera, and how the and the change in the error dynamics of the system, right? So now the question is, what is this LE, right? And also, it's not just E dot that we have to worry about. We have to find the relationship in VC and E, right? The error, not how the error is changing, but the error itself, right? So what we have to do is now kind of take this equation and kind of figure out the relationship between VC and E instead of VC and E dot, right? So what we do is we try to model this E dot, not E dot, we try to model E as a exponential function, right? Because we want the error to exponentially decrease, right? So what we do is we say E is equal to E minus lambda t. This E is the exponential, this E is the error. So I'll actually call this ER. That's actually terrible notation on their part. So this is ER, this is the error term, right? this is the exponential, as in the exponential function e to the power whatever, right? So you can see that we model the error as an exponentially decaying function, right? So what is er dot? Er dot is actually going to be minus lambda into e minus lambda t, right? Because if you differentiate an exponential function by time, you just get the exponential function back, and this lambda just comes as the coefficient up in front, right? So from this, what we see is e dot r is actually equal to minus lambda e if we want the error to exponentially decay. Er, sorry, right? Because this term is the same as e r. Is that clear? Before I move forward, is that confusing, or because if that part is confusing, it's going to be difficult to follow along. Did anyone find that confusing? Guys? Yes or no? Is everyone still here?
Yes.
Okay, so was that confusing or easy to grasp?
I'm still wondering what the aim of
So the aim is to find a relationship between the parameter that we can control, which is the velocity of your gripper, right? You want to find a relationship between that velocity and this error term, right? Because this error term tells you the difference between where the features are right now, which is this term, and where the features should be, right? So this error term, it's kind of like the PID, right? So if you understood the PID, this kind of helps you kind of understand, right? Because what we are trying to do is we're going to control the velocity, right?
So this
Based on the error.
this formula is calculating the relationship between the where is the gripper and where is the feature, and find the how to control the gripper to the feature, right?
No, so the error is between two features, right? So where the feature is now, imagine like if the gripper is far away, right? So if the gripper is over here,
Okay, so error will,
and the object is over here, it will look like this image one, right?
yeah.
So from that you'll have a set of features here, right? But you want the gripper to be right at the object, which is image 2. So then the features will look like this, right? When the gripper is right at the object before it picks up. So S star is where we want it to be, which is our reference, but it's actually at S, right? So there is an error between where we want it to be and where it actually is, right? So that is the error term, right? So just like in the PID control, we are looking at the output, right? The output are these features, and we are seeing that the those features are not exactly at the reference place we want it to be, right? Which means the gripper is far away, right? But then as the gripper comes closer, like this, what's going to happen? These features are going to move closer and closer to this, right? So then the error becomes less and less. Yeah.
Okay, so do you mean if the error is big, so the distance from the gripper to the feature is big, right?
Yes. Yeah. Pretty much. Right. So when obviously, right. So if the error is big, it means it's not where we want it to be, right? So this is why we like it depends, right? What your reference is. For example, if you want the gripper to be far away, right, your reference would look like something far like. All I'm saying is you have a goal set of features where you want your gripper to be, right? And then you compare it with where it is right now, and calculate the error between those two, right? And what we are trying to do is we want to decrease that error, right? Which is we want to decrease that error by controlling the velocity of the gripper.
So basically,
Yeah.
this is nothing but PID control for the end effector or the gripper.
Kind of, but it's a bit more complicated because we are looking at features, right?
I want to know the okay.
We are
what
looking
the
at
coordinates
features,
of
not directly, and so we need to like we need to understand how those features like how those change in the features when you're moving is affected by the velocity, right? Because if we blindly do a PID control, for example, let's say S minus S star, we see that there is an error, right? If we just blindly multiply velocity by this error, if we say velocity is just equal to P times this error, right? The thing is, in a gripper, you have a sixth of you can control the velocity of the gripper in the x direction, y direction, z direction. You can control its rotations and all that stuff, right? But the relationship between this and the error is not a direct, what do you call it, a proportional relationship like this, right? Just because you multiply this error by a proportional value and equate it to the velocity, it won't go to where you want it to. It will just increase the velocity in different directions, right? So we need to intimately understand how each of the like the error in these features are directly related to each of these components of these velocities. Does that make sense?
Yeah.
yes. So can I ask, the coordinates of feature is 2D position.
Exactly, right? So the like these features could be anything, right? So it could be 2D coordinate values, it could be an entire patch on an image, right? And just because there's an error like that, how that relates to each of these components in these velocities depends
Can it
on
be a
this.
3D?
Yeah, depends on this L matrix, which shows a relationship between velocity and the features, right? So that's what this L matrix is, right? It shows a relationship between the camera velocities and how those features are changing, right? So this thing is something we can figure out based on what our features are. We'll get to that, right? But on a higher level, what we want ultimately is the relationship between this VC and the error, right? And that's what we are trying to derive first. Like, what is the relationship between VC and this error? And then if we find that relationship directly, we can use that to control it, right?
Okay, I have one more question.
Yes.
If we want to something like related with my project,
Yeah.
fetch robot, right?
Yeah.
It has a arm.
Yeah.
An arm. Then if I give the fetch robot a 3D coordinate, do I need to implement this approach to let the robot arm get that point? I mean, it's gripper to get that point, get that 3D position.
So you're saying if you figure out the 3D position already in the image,
Yes.
and then you tell the gripper to go just to that 3D location, no,
Yes.
you don't have to.
Yes, I don't have to.
You don't have to.
Is that because this approach has been encoded in the robot control system, right?
Yes, and also what you're doing is you're not kind of controlling it in a step-by-step fashion there, right? You've already decided where to go to, and you're just directly, there's no feedback there, right? You've already predetermined what the location is, and you just tell it to go there. But imagine the object is moving, right? So at each, like for example, in your situation, your person is stationary, right? So you already decide, okay, this is the 3D location of the person. I should now move the gripper there, right? But imagine at each step the person is running around, right? And then your thing has to kind of follow that person and try to grab the person, right? In a situation like that, the features are changing and like the control is changing, and you have to kind of think about it. Or like for example, even if the person is stationary, right?
Okay.
You can incorporate the detection part into the control itself, right? But what you're doing now is you're assuming that your final what you're doing now is this, no, you're first detecting the person, determining his 3D location, and then telling the robot to go there, right? But that is assuming that the initial detection is 100% correct, right?
100% what?
Correct. That
Oh,
you've
yeah,
detected
correct.
the
Yeah,
exact location of the person, and you are telling the gripper to go there without any feedback, right? So it's kind of like saying, I know where the person is, like whatever method you use to detect the person is 100% correct. So if I tell the gripper to go there, it will perfectly go there to that person's location. But in reality, whatever detection that you do in the beginning, there is no guarantee that it will be 100% perfect, right? Because every sensor is noisy,
Yeah.
right? So how you would normally actually do this is at each step while the robot is moving, right? You would constantly check where the person is, right? And you will have a feedback loop back into your controller, constantly checking, okay, am I close to that person? Am I close to that person, right? Until you actually reach that person, right? In which case you will have to implement it like this. Yeah? Which is much more robust, right? It's a better solution because it is incorporating into the control itself a constant feedback loop of checking where the features of the person are. That means even if the person starts to move, this thing will start to track that person. While as in this case, you initially detect, you assume that it's 100% correct, and then you tell the gripper to start going there. If the person decides to just move a step this way, it will still go there. It doesn't know that the person has moved or anything has changed, right? So here the movement itself incorporates the change in the features. Okay? So visual serving is quite a complicated thing to do in real life again, right? As you will see, right? First, let's derive the equations and see if you guys can kind of get a basic understanding of how to derive the equations, and then we'll actually do an example and see how to implement it on a very simple level, right? So again, what is our goal now? We're trying to find a relationship between the velocity of the robot arm, right, which is a 6-DOF velocity, right? So v is actually equal to linear velocities and angular velocities, right? So there is a vx component, vy component, vz component, omega x, omega y, omega z, right? And we are trying to find a relationship between this velocity and this error, right? What is this relationship, right? Okay, so far we have a relationship between the change of the error and the velocity, right? And how did we do that? We first took this equation, which is the relationship between the velocity and the change in the features, which is something that we can derive, right? Which we will derive later in the second part of this. But this is something we can get. We can find the relationship between the velocities and s dot, right? And that is captured by this LS matrix, right? We'll try and figure out this LS matrix later, but for now, take my word for it, this interaction matrix, we can estimate it, right? But what this interaction matrix gives you is essentially how features are changing with respect to the velocity of the camera. What we want to do now is find the relationship between this and the error term. So to do that, you can see here that there is a s dot. So if we can create a s dot in this equation, we can kind of relate these two, right? So to do that, we just differentiate this and then we get s dot. And we can see that e dot is actually equal to s dot. So we can just replace this s dot by e dot, and then we get this relationship, right? But the next step is, how do we take this e dot and turn it into e instead of e dot, right? To do that, what we do is we want to find that relationship under the assumption that e dot or e, the error, is an exponentially decaying error, right? Because we want this error to ultimately decay, right? So we set e to be equal to the exponential function minus lambda t, right? Here it's a bit confusing because we are using e multiple times, but this e is actually the error. So I'm going to say er, right? Just to avoid confusion. Just to say that this is the error term. Error term, we are going to model it as some sort of exponentially decaying function. So what is er dot? Is just minus lambda e minus lambda t, which essentially means e dot r is actually equal to this constant times, what is this term? This term is the same as the error term, right? So e dot r is actually equal to lambda times er. So now we can get rid of this dot by just replacing er dot by minus lambda er, right? So what we can do then is we can say that this is actually equal to minus lambda e, or like er, equals le v c. Cool? Right? So let me erase all of this. What does that mean now? We have, if we take this equation 3, we can rewrite this equation 3 as simply minus lambda e into le v c. Cool? Because e dot is equal to minus lambda e. And here what I mean by e is er, okay? Not the exponential function e. Alright, so now we have this relationship between finally the error term er and vc, right? But since vc is what we can control, we try to make vc the subject, right? So to make vc the subject, we have to remember this le or ls, both of them are the same, is a matrix. So we need to find the inverse of this matrix to multiply onto this side, right? Lambda is some sort of constant. It's the time constant of how quickly we want this to decay, right? So we need to find this inverse of LE, but you will find out later on that LE is not a nice square matrix that we can find an easy inverse for. So we have to go for something called a pseudo inverse, right? And assuming that we found that inverse, we multiply this side by the inverse and this side by the inverse, and we get this equation minus lambda LE. LE plus is that inverse that I'm talking about into E, right? So we've just subjected VC in this equation by finding the inverse of LE, right? The inverse of LE is not very easy to find. It's called a pseudo inverse, right? And to find the pseudo inverse, you have to use this function. Right, you multiply by the transpose and then you find the inverse. It's called the Moore-Penrose pseudo-inverse, right? So finding this inverse is not that easy, but point is we can now get a relationship between the velocity and the error term straight away, right? But for that we'll need to find the inverse of your interaction matrix. Again, what is this interaction matrix? We will learn in a bit, okay? But point is now we have a direct relationship between the velocity of the gripper and the error. Okay. Another important thing is this interaction matrix. We again can't find that perfectly. Usually we can only estimate it. So we put this hat on top of it to show that it's not a actual value, it's an estimate, right? But yeah, this is the control law, right? This is basically saying that your input, right, should be your input value is related to your error value by these two parameters. So it's kind of like PID, right? But the value that you kind of multiply it by is a much more complex kind of situation, because this error value is given in terms of the features, right? It's not given in terms of the states, if that makes any sense, right? Because usually in a nice LTI linear time system or linear linear time system that we saw, the relationship between the states and the output are very direct, right? Here, the reason why we have to go through this complicated thing and we can't just do a simple PID is because that error term is there's no direct relationship, like the states here are not very clear, right? It's we are dealing with features, and features could be anything. It could be a Harris corner, whatever, right? Pixel values in a 2D image and things like that, right? So ultimately, the relationship between the physical control input, which is the velocity of the gripper, and the error values are slightly more complicated, right? But the important thing you need to understand is we now have a relationship between the velocity and the error, right? So this can be used to control the system. If the error is very high, this term LE plus hat will translate that error nicely into velocity values for us, right? So now comes the question, what is this LE value, right? Like what is interaction matrix? So that depends on what our features are, right? But we are going to assume in this case that our feature ultimately are 2D pixel values, right? So image coordinates like this. This will help us kind of derive the LE value very easily, right? So remember the relationship between 3D points and 2D points, right? So if this is our 3D point, how it's going to represent in the 2D point is like this, right? We learned that in camera projection, right? So we have a relationship between 3D points and 2D points in an image, right? And if we differentiate that, we get this set of equations, right? And how 3D points are related to 3D velocities are given by these set of equations, right? Again, I won't go into how to derive these, right? But it's basically spatial equations, right? There's linear velocities, angular velocities, and it relates how your 3D velocities are related to those 3D points, right? So if you look at here, you can see that rotations and linear velocities are related to each other in this way, right? So this is a relationship between 3D velocities and 3D points. Here we have the relationship between the 3D point velocities and the 2D velocities. So combining all of this, you can get a nice relationship between the 3D velocities and the 2D velocities, right? Which is ultimately what you want, right? Here you have the 3D velocities here and the 2D feature velocities here, right? So by taking out the 3D velocities out of this, you can put it into a matrix form, right? So if your features are described as just 2D points like this, right? What this means is those 2D point locations in your image, their velocities as the gripper moves is related to the gripper's velocity by these set of equations. Sorry, these set of equations, which put into matrix form looks like this, right? And this is what the derivation is, right? So you can spend some time looking at this derivation, but ultimately, like if you actually want to just implement it, you can use this as your LX matrix, right? So again, what does the LX matrix do? Originally, what it's doing is it's mapping your 3D velocities to some sort of features, right? If those features are directly just 2D points on an image, right? This is what your LS matrix will look like, right? Now, why is this an estimate? Because you can see here, to do this relationship, right, you have to, you need focal length values, you need principal axis values, and you do that using calibration, right? And in calibration, you guys probably realized already, you don't get perfect answers. You get estimated answers, right? So this entire LX is actually an estimate, right? So that's why we put that hat here. So now we have that LX matrix, right? And you can find the pseudo inverse of it, plug it in here, right? And then at each step calculate the error, and it will tell you what your velocity should be, right? So depending on how many features, so if there is only one set of 2D points, you will have this, but if you have two sets, you'll have another layer of this, and so on, right? So typically, if you want to do a 6-TOF control, you need 3 separate points. So your LX matrix will be this in 3 layers, right? Okay, so I know this sounds very complicated, and it is complicated, right? Visual servoing is a very complicated thing to achieve. So you can read through this again, watch the video of this again. I hope the explanation is enough for you guys to actually do the question and try and implement something like this. But this entire document, just read through it. Again, you can do an entire course on visual servoing, but this is a very brief introduction to it, right? So that it can help you move forward with your projects if you need to actually implement something like this. Okay, so we'll actually do a question, and it won't be that, like, you will notice that realize that it's not as complicated as you think, right? So I'll give you guys like 2 to 3 minutes to try question 3, and I'll actually do it with you guys before we wrap up today's class, and then hopefully it'll be a bit more clear. Okay, guys, can you see my screen? Let's just quickly do this question. So what's happening is we have an object that we've detected, right? And the question is, what should be the, so imagine the gripper is on top of this object, right? And basically what we want to do is we want to move this gripper so that this object is at the center of this image, right? So it says here, calculate the camera velocity vectors for each case such that the squares obtained by the end effector mounted camera are centered and all the edges are parallel to x and y, right? So we have three different images. So for example, in this image, let's take image 1 first, right? So if we want this square to be nice into the center, we want the gripper to move this way, right? And kind of come closer to this image, right? So we need to find the velocities that will create this image to come to the center, right? So first we need to detect this image, like features in this image. So what we do is we load the image, and the best thing we can use is the Harris corner detector, and we look at the location of those features. So if I just run this section, you can see that these are the four corners of the image that we are getting, right? Now to implement the control, first we give the intrinsic parameters of the camera, right? For the principal points, I'm just going to take the center of the image as the principal point, right? And the distance, yeah, so imagine the distance from the gripper. So if the gripper is like this and the object is like this, is about 50 pixels, right? 50 since the units in this, you'll be dividing everything, it doesn't really matter. So okay, let's say 50 meters or whatever, right? So the z value, the distance away from this is 50 meters, right? That's a bit unrealistic value, but you can't expect this to be 50 meters away, but imagine it is, right? So we have a z value as well. The lambda value that we're going to pick is 0.1. That is basically the decaying of the error that we're picking, right? And the principal point is the center. The focal length is 400 by 400, right? So we have all these intrinsic parameters of the camera here. So now we have the first image. We found the four corners of this image using the Harris corner detector. That's where it is. Now we have to set the goal location or the reference value that we want it to be, right? We want it to be right into the center, right?
Oh, hi, Mali.
Yeah.
Sorry for interruption.
Yes.
So for the z value is the distance between the gripper to the.
Yes. So what are the equations that we have here? To find the relationship between 3D points to 2D points, we need the projection, camera projection, right? In camera projection, you need the distance, you need all three values, right?
So the z value means distance or means above the cube.
Yes.
So it means above the cube, right?
No. So z value is with respect to the camera, right? So in camera projection, so you need to worry about which reference frame you're looking from, right? So remember in camera projection, right? Z is this value. Right now, our reference frame is the camera, right? And the camera is attached to the robot, like this, on the arm. So it's attached right here. So the z value is along the camera's principal axis, right? In our quiz question, we had the camera attached onto the top, and we had the robot arm like this. So the z value was
I see.
that, right?
So
So
z value, whatever the robot is, z value is the distance between the cube to the camera.
wherever the camera is, right? So
Yes.
yeah, because we're using the camera pinhole model. So if we looked at the camera pinhole model before, the projection equations to project it to a 2D image was the distance from the camera's principal point to the object, right? So the z value is along the camera's axis. If we are going to look at the projection equations to do this, right? So we now know where the current location of the image is, right? We want it to come to the center, right? So the image is a 1000 by 1000 image, right? So the center, if you put this roughly in the center, right? So it's a 1000 by 1000 image. You can pick where it can kind of appear right in the center. What we can do is we can pick 250 here, 750 here, 250 here, and 750 here, right? Sorry, we can pick point 250 by 250, 250, 750, 750, 250, and 750, 750, right? If we pick those two, these 4 points, it will nicely come into the center, right? In this 1000 by 1000 image, right? So we kind of pick this as the target. It's up to you to pick whatever target you want, as long as it nicely comes into the center of your image. And because right now, what does it look like? Right now the image is somewhere like this, right? And we want the gripper to move so that it comes into the center like this, nicely in the center like this, right? So as long as you can pick some values here that will put the image in the center, that can be your target, right? So I picked these values, 250, 250, 250 by 750, right? These are going to be the targets, right? And if I look at the current location, this is what the current location looks like. Right? That's what we got from the Harris corner detector, right? Forget about this for now. This is the second image, right? So you can see here that if I run the Harris corner detector, I'm getting the current location, the observation. This is what the observation is. This is what our target is going to be, right? So this is S star, this is S, right? So this is 250, 750 and all that. If we start looking at the image from this point, right, as the image reference frame, but obviously there is a principal point of the image is here. So we need to, again, this goes back to the camera projection equations. We can convert that by saying minus p and dividing by f. It will give you the coordinates of the location with respect to the image plane, right? So now we convert the observations and our target. So I call this target xy, right? Relative to the image plane. Then what we need to do is figure out this LX matrix for each of these 4 points. So we have 4 points now. So LX has to have 4 rows of these set of equations, right? So I've just created a simple MATLAB function here called function LX. You can see here, if I open that, it just creates a LX matrix, which is essentially this matrix, right? And the first term is minus 1 over z. The second term is 0. The 1, 3 term is x over z. The 1, 4 term is xy, and so on, right? So what I've done is, right, I've created a function. If you give the x, y, and z values, it will give you the LX value, right? Basically this value, right? So I've just created this matrix in this function, right? So to call that function, I just have to give x, y, z, and it will output this LX matrix. So we kind of have to do that for all of those 4 points, right? So I calculate the LX matrix for all of those 4 points by just running it over each of those 4 points, right? So if I run this, just show you. size p now. So now you can see that Lx looks like this, right? The first two columns are for the first two rows are for the first point, right? So this matrix, right, is basically this, right? And I've done that for all four corners, right, by putting that into a loop. So now I have my full Lx for all my features, right? And then I just have to create the error term. The error term is my observation minus the target, right? But you can see if I subtract these two, I'll get a 4x4 matrix. I need to put that into a long vector. So I use this reshape function to do that, right? This de doesn't matter. And then what I do is, remember, ultimately what I want is not Lx, I want the pseudo inverse of this Le value, right? Or the combination of Lx, which is what is Le, right? But I don't want Le, I want Le plus hat, which is the pseudo inverse of Le. So I have to do this operation to get the pseudo inverse. So that is this line, right? Once I do that, the velocity of my camera or the velocity of my gripper is just simply equation number 5. So I multiply Lx2, which is the pseudo inverse, into lambda, which is given here, right, into those errors, and finally I'll get the velocity. So if I run this, for example, you'll see that this is the set of velocities I need to give to my camera, right? And you can see that there is no rotational velocities, there's only linear velocities involved here. Why? Because if you look at this image, it just looks like this, right? So for me to put it right in the middle, I just have to do a linear set of linear velocities like this, right? There is no rotation involved. I just come like this, move. If I just move the camera, if I just move the gripper, like if the gripper is here, if I just move it this way, I can nicely get the image in the center the way I want it to, right? Does that make sense? Because if it's here, the linear like the camera has to move this way, right? So you can see here that the velocities are minus in the x direction, minus in the y direction, and in the z direction there is a small positive velocity as well, because we've not only moved this way, but we've kind of zoomed in as well and made sure that our image is at 250 250, 250 750, 750 250, and 750 750, right? So by looking at these velocities, you can see there is no rotational velocity involved, just a bunch of linear velocities. But if you do the same to image 2, right? So image 2, you can see here image 2 looks like this. If you run the same thing for image 2, you can see now we have now we have a small rotational velocity involved in the z direction as well, right? Because this not only has to move and put this into the center, now it has to also rotate in around the z-axis, because the z-axis, imagine the z-axis to be coming out of the screen. It has to now rotate this image also, so that it can nicely come and create an image like this, right? So I'll put, I know I kind of rushed through this a bit and there's a lot to cover here, but I'll put this code up and you can have another read through this document. And again, you don't have to worry too much about this unless you're trying to implement it. If you're trying to implement it, you'll have to read through this a lot and try and understand it. and I can help you some more if you want to implement it in one of your projects. But this should give you an idea of how to do some form of visual servoing, right? So that's it for today's class, and that's it for the tutorials. Finally, I'll put up the answers. This document is also online in Canvas. If the explanation wasn't too clear and you have any questions and you're trying to implement this, we can have another session about it maybe next week. Because from now on, every Friday we'll have classes, but we won't have any lectures or tutorials. All we'll be doing is discussing our projects. So from next Friday onwards, it'll just be a project discussion. Yeah.
Hi, Malik. Could you explain a bit about the velocity, the values in the velocity matrix?
Yes. Okay.
I mean, in the command window,
Yes.
VC matrix.
Yeah.
I'm not sure the last three values are the rotation matrix.
No. So let me re-explain. Right. Let's look at image 1 because that's easiest to understand. Right.
Okay.
So what does image 1 look like? It looks like this, right?
Yes.
So
no rotation.
no rotation, right? So it looks like this. We just have to bring it here, right? What is our velocity vector? Our velocity vector contains Vx, Vy, Vz, right? Omega x, omega y, omega z.
So this omega is roll pitch or something.
Yeah, roll pitch yaw. Yeah. There's a rotation around the x-axis, rotation around the y-axis, rotation around the z-axis, right?
I forgot. So x is roll, right?
Sorry?
X is roll. Y means pitch, and z is roll. I forgot it.
Yeah. So this will be roll,
Okay.
pitch, and yaw, right?
Okay.
So when you look at this image, right, none of these need to matter, right? Because it's nicely on top of the image already. All you need to do is if if you're looking at it this way, the camera of the robot is, so if the object is like this, right, to get this kind of image, the gripper has to be somewhere like this, right? Or the camera has to be somewhere like this. We want the camera to go here, right? So that it comes into the center. Does that make sense?
Yes.
Yeah. So imagine you're looking at a cube from the top, right? Imagine you take your phone, right? Actually, right? Imagine there is a cube like this on the table, right? And you take your phone and take a picture of it from the top, right? You will get you get an image like this, right? So imagine to see an image like this, you should be right in on top of it, right? And kind of at an offset, right? Like if I'm looking at it from the top, the camera will be somewhere around here, right? But I want the camera to come underneath the object so that I can
We will need x velocity and y velocity.
exactly x and y velocity, and if I want to kind of zoom in as well, I need a z velocity. I need to come closer to it,
Okay.
right? So I need it to come like this. So there should be an x velocity, a y velocity, y velocity like this, and then a z velocity downwards as well, right? So if I run this, you can see that's what I'm getting. I'm getting x, y, z components. All my rotational velocities are 0, right? So I'm getting
So at this time, the camera distance from the the distance from the camera to the cube is 50.
no. When we're starting, it's 50.
Starting is 50.
Yeah, when we're starting, it's 50, right? And what we want is the target to be this, right? Our reference So when we are starting off, this is what the image looks like, right? And the distance to this image is 50. But when we want to end up is, so this is our observation, this is our target or our reference, right? So we want to go from here to here. So if the image looks like this now, and when it goes here, right, you can see that the square has also enlarged, right? Because we come close to it, which means the z distance becomes less.
Do we know the time? What's the movement time?
No, all we've calculated is what is the velocity that we need to apply from this point to this point. We haven't actually done this yet, right? We are just calculating. If I want to get this, right, if this is my target, what should the velocity of the robot be to get it from here to here?
Okay.
Yeah? And then we have to actually apply this velocity and move it there, right? But we are doing that at each step. We are at each step getting this new observation and then calculating this v and then implementing the v and then again getting a new observation, calculating the v and implementing it until it reaches this target, right?
So all the approaches,
I can't hear you
all the
properly. Can you
approaches
come
get
closer to your mic?
velocity, right?
I can't hear. Yeah, can't hear you clearly.
So I mean the final result is just the velocity, not,
Yeah.
not related with time. So if we want to control the robot to reach the objective point, then we also can build a loop to implement this velocity and check step by step. So
Yeah, the
whether
observation.
the
So
quicker
usually,
is
usually you have to keep observing, right? So what you would do is, this is the first step. This is where it starts. You give a velocity based on this error. So now there's an error, right? This is where you want the target to be. This is where the observation is. So you will calculate an error between observation and target. So based on the size of this error, you will determine this velocity, right? Because the equation is velocity is equal to minus lambda LE times this error, right? So that will be the first iteration. And then this, while this is moving closer and closer, right? While this camera is going from here to here, you will do this constantly. You will keep observing, generating an error and generating V, right? Because then what would happen is, for example, if you come close to it and overshoot it, right? So this is where you, let's say this is where output should be in the X direction, and this is where your output should be in the Y direction or whatever. Sometimes in the X direction you might overshoot, or in the Y direction you might overshoot. So if you're constantly looking and constantly observing, you can kind of correct those things and come to the where you want to, right? So you have to keep doing it, right? So this is just the first iteration of that, right?
So is there any possible that the V matrix, all the values in the V matrix is zero, or just near to the zero?
All the values in the what matrix?
In velocity matrix.
Yes. So yeah. So what happens now? What is your velocity? It's equal to minus lambda LE into the error, right? So when you keep coming closer, what's going to happen to the error? What is your error? The difference between the target.
So approximate at zero.
Yeah, when your observation reaches the target, your error becomes zero, and then your velocity becomes zero, right? So it's like as the error becomes smaller and smaller, so the more you come close to it, right, this error becomes smaller and smaller and smaller, and your velocity becomes less and less and less, right? So if you are really far away, right, so the object is like this and you're really far away, your error value is going to be very high. So you're going to have a very high velocity, right? And so it's going to start moving faster and faster closer to your object. But as you come closer and closer, your error starts to decrease, right? As your error starts to decrease, your velocity starts to slowly decrease. And and eventually where you want it to, it will stop, because then the error will become 0, right? And then your velocity will finally become 0, and your controller will stop moving the arm.
I mean the absolute zero. I mean maybe the robot arm has some tolerance that the target minus the objectives maybe not zero, maybe just near the zero, but not the exact zero.
Yeah, in a real world system, obviously you can't get perfect values, but what you're going to do here is you're going to keep moving V until it reaches 0.
So can we build something like use condition if the value in a very tiny range, something like light but bigger than minus 0
Yeah, you can
0,
stop.
0,
You can
1,
stop it
and
completely if you want to.
something like that. If in this range, then the velocity matrix will be 0.
Yeah. It's up to you to set up. So those things are called heuristics. It's like you can decide certain conditions if you want it to stop, because if you implement this and you realize that this thing can never reach 0, and then it comes close to this object and starts just like moving little and just like oscillating like that, then obviously you can set some sort of condition to stop that from happening, right?
Oh yeah.
Which is why
Yeah.
like understanding how like the output behaves is important, right? So if it starts oscillating like this, and like we need to make sure that the system has some sort of stability, right? And if it isn't in this kind of situation, like you said, you can create some sort of heuristic, right? Which is like some sort of condition where you can say, okay, once it comes close enough, I can stop it.
Because when I was doing the quiz 2,
Yeah.
we use the support package of name A5 support, something like that. You know that? Like
I can't hear you properly, man. You're very soft.
hello? Hello?
Yeah, can you come closer to your mic?
Oh yes, I will. Okay.
Yeah.
So when we was doing the quiz 2, we use a support package named A5.
A5.
Yes. We simulate environment in the skeleton, maybe.
Okay, I haven't really used it. So?
So I use the audiometry data and sensor data
Yeah.
to find the closest point relative to the robot in the sensor data.
Okay.
Okay, then the robot needs to face the closest point.
Yeah.
And it needs to face to it
Hmm.
and stop it. But when I found that, but what I found is the robot won't be stopped exactly.
Yeah, I
Be
mean,
something like shake all the time.
yeah,
High
yeah.
shake if you zoom it.
Yeah.
So that's what I mean. So
Yeah.
I think
So
about the
in a
robot
situation
arm
like
will
that,
have the same situation.
yeah, you
Right?
can see that in all of this, like there's a lot of approximation that takes place, right? This L hat is an approximation. It depends on how accurate your focal length is, and that is obtained through calibration, and the calibration answer is never 100% perfect. It's an estimate. So you, in real world scenarios, that's what I meant before. So when we were discussing PID control, like and talking about Fuzzy's project as well, like in real world scenarios, what you learn when you keep learning engineering is that nothing is perfect. There's a lot of noise, all that stuff. So you can't. All of these equations are just ultimately approximate models of the real world, right? It doesn't take into account all the random noise and issues in the motors, issues in your sensors, none of that, right? So what you do is you implement something like this, and then you have to add some sort of other like heuristics to kind of control it. You try to tune parameters so that it ultimately does what you want it to do, right?
Okay, so what's the meaning of the height? Sorry, I forgot it.
Sorry?
What's the meaning of the height? The height above the
It's an estimate. It's not a,
Oh, I estimate. Okay.
yeah,
Okay.
it's an approximation.
Above,
Yeah, this hat, right?
above.
It's an approximation, right? It's not the real value. It's just an estimate, right? It's an estimate because I can't hear you.
So I mean, all the height means approximation.
Yes, it's an approximation. Why is it approximation? Because in the calculation of L, right, to get these values, you have to use focal length, you have to use the principal point values and all that stuff, right? And none of those are perfect. They're just estimated values, right? So because of that, your ultimate L value will be an estimate, not a perfect value. Yeah.
Yeah. Thank you.
All right, so we'll wrap up for today then.